Okay, so hello everyone, welcome. Thanks a lot for joining us today. I would like to start with just very two fast things. The first one is that I tested positive of a coronavirus a few weeks ago, so then my voice is not still as good as it used to be. And probably I will cough a bit during the class. So if you see that, don't worry, I'm okay, but it's just that I'm still in recovery mode. And then the second one, I think that is the most important one, is that I really appreciate that you are joining us, not only on class, but also watching the YouTube videos, because I think it's very nice to have your support and to see that you are interested on these tutorials. So it really encourages us to continue doing them, and I really enjoy your support. So thanks a lot. And today we will start the main course. So you remember we started with DeSIRe, then we moved to RH, and now we are finally reaching this side. So I think it's also a good milestone that we have achieved after almost 1 year of tutorials. And I'm really excited for starting this final piece of the big picture. So let's start. The aim of this course, so you will see that some of the slides are recycled from the first class that we had on March last year, because this was a combination of DeSIRe and some proposals that we had. So the idea is that we want to learn how to use DeSIRe. I will always call it DeSIRe because, as you see, the name is a bit long. It's the departure coefficients Stokes inversion based on response functions. So I will just say DeSIRe. And the idea is that we will cover the main things that the code can do. So it's synthesis, computation of response functions, and inversions. We will try also to work a bit with MSD simulations. We did that with the DeSIRe online course and with the RH online course. So most of the things are already covered, but we will learn the last part of the steps we need to adapt a bifrost snapshot to DeSIRe for running synthesis. So basically it's what we did with RH, but then we need a final step that we will cover in the class. Then this is what I said last year, so I will just go a bit quickly, but basically I would like to teach you how to do a lot of things that I have learned to do in my previous years, and is related to compare simulations and observations. Then we need to solve the right transfer equation and synthesize profiles and then compare with observations. Also, to reproduce spectral signature of physical events. So you have a simulation that you're interested on analyzing, you solve the right transfer equation, you generate profiles, and then you try to relate the physical phenomena that you have in the simulation with the spectral signature that you see in the profiles. Also, this can be related to study the possibility of observing those spectral signatures on a given observation with a given instrument. Then, as I said last year, this is a seed for multiple things. It could be improving the simulations. So if the spectral signatures that you see when you synthesize profiles are not realistic, then maybe something is missing in the simulation. If you see that they are realistic and they are consistent with what you expect, then you can use it, in fact, for performing observations specifically oriented to determine those things. Then you can also learn a bit more to analyze observations based on the theoretical studies. And also something that I think is very important is that if you have a configuration that based on your theoretical studies is really good, and you cannot do it today, it's a good thing that you can write down this and in fact evolve a bit this work to really propose a design, maybe an instrument, maybe a telescope. So all these things that I've done and I'm doing still today is something that we covered in DeSIRe and RH courses, and of course we will do also here. So I think it's something that I hope it will help you to do multiple things that you can be interested on. So This is something from last year, but again, if you are not interested on SER or you cannot check it, I think it's good to bring the people working on this side, because this is in fact the DeSIRE tutorial. So we are a few, and then let me just show them to you. The first one is David. He's really good. He's a really nice person and very clever, and he knows a lot of things. He was doing a lot of inversions in his early years of career, and now he's doing a lot of instrumentation and management, so he has knowledge of a lot of things, and he's really nice to work with, so it has been a very good thing to be able to spend time with him. Then Basilio, he's very nice. He's not so young anymore, so look at the video, don't look at the picture. But he's also very clever and very nice, and he was one of the let's say fathers of these inversion codes that we use these days, and he was in fact the person behind SER that has been a really successful code, and he's the one that has code design. So he's the one really programming in Fortran 77 inside the code. So then you also have Han, that well, he's closer to the picture than Basilio, but but also in the picture he's a bit younger than now. And again, he's also really clever and knows a lot about varieties transfer. And he was the one behind RH that I think is one of the best codes that you can have for solving the variety transfer equation in non-LTE, and has been also working on updating and upgrading RH specifically for design. So it's also a very good thing to be able to work with him all this time. Then Ricardo, he's not able to be here today, but he will be in the next days. Also very nice person and very clever. And he was the one responsible of creating Python parallel wraps to make the DeSIRE be able to work on parallel. And then in fact, he decided to implement those packages also on RH and SER. So everything related to parallelization has been on Ricardo's side. And then we have Esperanza, that she didn't have a picture last year, and she's not going to have it this year again, and I think never. So just she's very good. She's a programming expert, and she works also at IIC, and she has been in fact the main driver behind having a bit more structure on the code and less bugs. So most of the bugs that Basilio introduced, Esperanza was checking them. Han also introduced some memory leaks that Esperanza was checking them. So I think she's one of the main drivers of making DeSIRE working as best as possible. So she's crucial also for the project. And then as I said last year, so all they are responding to me, and I'm just trying to make all these pieces working together and interact between everyone and have everything consistent. So essentially just trying to make it work. Okay, so then let's continue. Again, general concept, I think this was probably from last year, but just very quickly. So the code is based on SER. So then just let's try to quickly remember what SER is. So it's an inversion code that works in LTE, in local thermodynamic equilibrium, and it uses analytical response functions because they are easily defined in LTE. It's very fast and reliable. So reliable because it has been more than 20 or almost 30 years. I think 30 years. This year will be 30 years because it's from 1992. But the idea is that when you move to chromospheric lines and you want to fit them properly, then you cannot work anymore in LTE. So then you need to include the non-LTE approximation in your code. And then the idea is that there are several codes, inversion codes that can do that. So for example, you have Nicole, Snappy, and Stick. But all of them are very computationally demanding. So and this is mainly because response functions are computed numerically by finite differences, or in the case of, I'm sorry, in the case of Snappy using a hybrid approach, but in general, they are much slower than, for example, SER. So then a few years ago, I think around the end of 2017, we decided to try a different approach. And it was to perform inversions essentially in LTE, but including non-LTE effects through a correction, including the correction or deviation from non-LTE. This is what we call departure coefficients. So then the main idea that you can have is that is SER, but including non-LTE information that we get from RH. Okay, we will enter in more details later, but essentially that. Okay, so in that sense, it's a fast code, it's reliable, and it's relatively simple. Okay, so then I said in all the tutorials, I will try to not enter into many details in equations, something like that during the presentation. So I put the DeSIRe publication in the DeSIRe folder, so you can check it. In fact, luckily, or I don't know, maybe luckily, today we received a mail from Astronomy and Astrophysics that the paper is accepted for publication. So then the version that you will download today is, I think, the last one. So it's also good news because we are starting the tutorial in the same day that the official paper is accepted. So very nice, or very good, good coincidence. And the idea is that how it works is basically SER. So we have, for doing an inversion, we have a data that we want to fit. We start from an initial atmosphere. We perturb this atmosphere in a specific locations. 1 second. Just 1 second, Ryan. Please, everyone, if you can just not use the chat, you can just ask me the question. You can interrupt me and ask me the question, because then the people that we will see the YouTube video later can see the question. So I think your question is where is located, right, Ryan?
Yeah, just where do we find all of the stuff, the code and the documentation and everything? Because I think I may have forgotten.
Yeah, no, it's fine. So every time that I will send the mail with information, so I will send it at the end, also with the link for the next class. I will also include the link to Dropbox. So there you just click and you will have the main distribution with the DeSIRe folders. And there inside the DeSIRe folders, you will have the publication and also today's class and everything. So don't worry, at the end of the class, I will always send a mail, and there you will have the Dropbox link to all these things. Okay.
Esperanza told me that today she was uploading in the GitHub DeSIRe.
Okay. Okay. Good.
Next week also
okay.
You can find that.
Okay. Good. But basically that, Ryan, and everyone. So all the content that we cover here, it's in Dropbox, and the link for that folder, it's always in the mail that I send at the end. Okay. And also that, so please don't be afraid to just ask me. I prefer to not read the chat, because also people that will see the video later will not be able to see it. So just interrupt me and then ask me the question. Okay. Yeah. So then let's move. So what I was saying is that the code will change the atmosphere in every iteration, and the idea is that it will try to obtain an atmosphere that, when doing the synthesis, produces a profile that is as close as possible to the observed one. And how the code, or how much the code decides to change the atmosphere, is based on the response functions. And those response functions, as we will see later, is essentially an estimation of how sensitive a given spectral line is to a change in atmospheric parameters at a given height. Okay, so this, we will check it later, but essentially that we start from an atmosphere, then we try to modify it until we get a profile that is close to the observed one, and these perturbations are done based on response functions. Okay, so then it's essentially SER. For those that has really checked the SER course or have used SER in the past, you will see that DeSIRe is going to be very simple, or very close to that. And for those that have not really be able to follow the SER course, don't worry, we will cover it slowly in this tutorial. Okay, and we added a few elements to SER. So as we said, we need to include a correction to take into account the non-LTE effects or deviations to non-LTE. So what we do is we compute the atomic populations in non-LTE with high accuracy with RH, and then we compute the deviation of those non-LTE populations respect to LTE, and this is what we call the departure coefficient. And this is added to the inversion with, let's say, DeSIRe module, and then we are taking into account those deviations, okay? And this can be done in parallel or in a serial mode, okay? So then again, don't worry if these things sound difficult or new, we will go again step by step. I know that maybe I refer to RH or SER tutorials during this series of videos, but still I think most of the things I will just explain them from zero, so then you don't need to really cover all those tutorials if you didn't have the time. Okay, so then we will start, in fact, today, just installing the code and running an example. We will do these things, and I will not cover them in detail, but basically synthesis, computation response functions, run inversion of those synthesis profiles, and then run inversions of reference observations. Then we will do the same in parallel. So synthesis of a 3D MHD snapshot, in this case, it will be Bifrost. We may also just learn how to do a computation of the response functions in parallel as well. And also we will run the inversion of those synthetic profiles starting from a different atmosphere and just to check how the codes behave. This I don't know, so I will just put it here, and it's a goal, but it's not mandatory. So one and two, definitely we're going to do them, but I don't know if we will have observations available, or if we see that it's very easy to show you how to embed with observations. So then if we have data, we will also dedicate the last modules to just work on data, because it's not the same as with synthetic data. So maybe here you need some extra step or be careful about some things. So just I will try to make it as a topic for the last classes, but I can guarantee that we will have the data. So just let's hope if we can have it. I think this I showed it last year, but I think I didn't cover it in the third course. I'm not sure now. So I put it here because I think I mentioned that I would like to show you how to transform MHD cube atmosphere, to transform it to different heliocentric angles and then compute the Stokes profiles there. So essentially here you have a sunspot that I computed the intensity at 500 nanometers, assuming heliocentric angle 1, 0.75, 0.5, and 0.25. So then it's like reproducing a disk to limb observation. I think I didn't cover that. So if yes, correct me, and if not, I will try to cover it in class. It will be something very simple because it's ideal procedure that Basilio prepared. But I would like to show you how to use it, and then probably you can also translate it to Python or other things. But this is something that sometimes you want to do, and it's not easy to find how you do it. So I think I would like to insert this in some class as some pause between very complex things and something that is a bit different and is probably more easier to understand. So I will try to also include this at some point. And this is what I was mentioning. So we will take the Bifrost snapshot. We will use RH for computing the optical depth. And then we will translate that optical depth plus a snapshot to the DeSIRe format. And then we will run synthesis with DeSIRe. And then we will embed those profiles. So then we can check how the code works for embedding, for example, this 2D area. Or we can do something like we did in the paper, that is, we make a horizontal cut, that is this line, and then we plot the cut, that is horizontal domain, this is X, and this is optical depth. So these are different layers. And we can compare the original temperature, line of sight velocity, and magnetic field with the one obtained by the code, that is the one below. And we will see that sometimes the code is really good, and sometimes we see some difference like in upper layers. And then we can check if those differences are the inversion configuration, the spectral selection, both things, or something different. But this is something that we will do in class, and is the main test that we present in the paper. Okay. So then today's course. Sorry for the long introduction, but yes, go to today's course. We will start with the basics. So today is going to be very slow and easy. So don't feel afraid. We compile the code. We examine the different folders that you have inside the code, just to give you an idea how it's distributed inside and what things you may need to check and what things you have to just leave it how it is. We run a simple test just to check that the compilation was done properly and the code is working on your computer. And then we will follow the basic steps that we have in CER. And this is for the next class. So is now we check that it works. Then next class we start with the synthesis and checking one by one all the configuration profiles that you need to change for the process. Yeah, I think Hars has a question.
Hi, Carlos.
Yes.
I just basically I have used Stick, so I wanted to little bit understand more about how DeSIRE works and Stick works. So my understanding is when Stick calculates the response functions, it stores departure coefficients, and then when it goes for inversions, then it uses those departure coefficients as a it initializes the population using those departure coefficient, and then it goes forward. So how does DeSIRe does differently? I do not understand properly how does DeSIRe works in an overall way.
Yeah, so I think the first thing is that I'm not sure how Stick works, but I think it doesn't use departure coefficients. I think it computes the non-LT populations with our age, and then it solves the response functions numerically by finite perturbations. And I think it's not using departure coefficients. So it's just full non-LT process. So I think this is the main difference. So the code every time it's computing the non-LT populations and then solving the response functions numerically, that it takes much more time. But I think departure coefficients are not involved in the code. If I'm correct, I have never used it.
Okay.
Yeah. So we are the ones that are doing the process that you described, if I'm correct. So
okay.
Yes. So,
all right.
Yes.
Yeah, well, one could say that departure coefficients are used implicitly, right? And we just use the straight non-LT population numbers.
Yes.
So for us, departure coefficients are just a way to translate easily non-LT to LTE quantities.
Yes. Okay. But I will try. Yeah, I will try to check a bit more if I said things correctly, and maybe next class we can cover it. Yeah.
But yeah, you're right, Carlos. The main difference is that the response functions are calculated numerically by finite differences.
Yes.
And therefore it takes much more time than the analytical LTE expressions enhanced with the departure coefficients that we are using.
Yes.
Okay.
Yeah. Thank you. Okay, so then I explained already what we are going to do today. I will keep this miscellaneous section. Today is the first one, so we don't have anything to cover. And then the next thing is the homework, so we will come back to this later. So then let's start with today's class. Okay, so then I think you can see this file. Okay, and then this is terminal, everything's working. Okay, so then the idea is you will have the DeSIRe code in the Dropbox folder. So here you have the link, but I will send it again also in the mail. So the first thing you need to do is just download a compressed file. So then compress the file in where you want to run it. In my case, it's in my server, and then I call it this way. So there's DeSIRe 2021, December 20. And then inside you will have these folders. Okay, so then let's go one by one. Okay, as Basilio said, Esperanza is going to upload it also to GitHub, so probably you will have it there. But the idea is that I will put always in Dropbox the version I'm using for the examples, because I think we will find some bugs. So then we will change it along the course. So every new version that we have, I will put it on Dropbox, and I will point every time that we run a tutorial and we run some examples, I will indicate which version I'm using, just in case the things change and we see some different results. Okay. So then you have inside these 7 elements. So let's go one by one. So in the case of this file, it contains binary files. So there, when you compile, you will have the DeSIRe executable, but also different executables that are used, like, for example, modelador. So we can just take a look inside. You have these things, and they are essentially executables for running different things. The code, in principle, running the code itself. Then in the doc file, doc folder, that is documentation, there you see that it's almost empty. We should have a manual of the code there, but it will arrive at some point. So now you have a very, very quick guide. But the idea is that don't worry, because the manual will be all the classes that we will have. So don't feel worry about that. So we will explain everything that you need, and eventually we probably will write a manual. Then you have a folder that is called IDL, and there you have some routines. I don't remember which ones are because I don't use them, but I think they are related to visualization purposes. And I hope at some point we will also have a Python folder that will be the same routines for visualization things, but writing in Python. So maybe some of you already have something in mind, so then you can add there. And then you have a README file. It's also very simple. In fact, it's not updated, so I will ask Basilio to update it. But basically, you have a very brief description of what I'm saying now, then how to install the code, that we will check it later, and how to run it. So there you have the main things that you need for just getting started. Okay, so then we have the run folder. So here is where you're supposed to put all the folders that you want to run. So if you remember, for example, with RH, we had RHF1D. And remember that I was putting all the folders where we executed things inside that RHF1D. So here is similar. So inside the run, you will have some folders. In the original configuration, all these folders are inside. This is for today's class. So then you will have all these ones. And they are different examples of synthesis and inversions. And the idea is that I think it's better to have all the runs that you're going to perform in serial inside those folders, because all the configuration files are pointing to general files that I will tell you where they are. So if you try to execute the code from somewhere else, you have to change a lot of paths in a lot of files. So basically, I recommend you to just run the code there as we did with RH. So we always were working in RHF1D, and then you simplify everything. Okay. So we will cover this later. So then we have the source file. So they are here. I don't know. I think it will take some time, but just click and then let's see how it goes. And there you basically have the code. So you have all the routines related to computing spectral lines, computing populations, computing everything. And if you want to check there, I think it's not necessary, but if you want to take a look, you probably will see that there are Fortran routines and also C routines. And Fortrans are because they are heritage from DeSIRe, and the C ones are heritage from RH. Okay, but basically, unless you want to change something about the code, that I think this is really expert level, you don't need to really get into that folder. Okay, in fact, there's a lot of routines, and you see that it's loading. So then let's move to bar, and here it's where I said that you will have a lot of let's say files, that configuration files that we use, but you don't change actively all of them during an inversion. So for example, imagine that you want to have accurate background opacities computed including a lot of atoms. So then those atoms, you are not going to change them during the inversion process or even during different processes. So those atoms are here. But the atom that you are going to actively change, I recommend you to put it in the example that you're running. But the rest of them, they are going to be here. And this is the same for all the files that you have. So for example, here you have in atoms, you have what we had in RH in the atom file. So you have multiple models and they are the standard ones that we use for background opacities. So then you don't need to change them in general. Okay. So then let's try to compile the code. I don't know if I'm going a bit fast. So is there any question up to now, or can I continue? Sorry. Okay, so then let's continue. The idea is now we are going to compile. So we are, as you can see, I'm inside this folder. So then you go to the source folder. Oh, sorry. The source folder, and then you type this. If you have an Intel compiler, you don't need to type fc = gfortran, but I think most of you are using gfortran, so then try to just type this. Then you will see that it starts. You will see that now it's calling gfortran and it's doing a lot of compilations, and these routines are most of them, they are from DeSIRe, and in fact they have sometimes Spanish names, so you can't be certain that this is DeSIRe. But then at some point we start with GCC, so now we are compiling C, and this is RH routine. So in this compilation we are compiling Fortran and C routines, and the idea is that the code will run until you reach this point. So I copy this just to allow you to check that you have something similar. And I think the most important part is that you see this living directory. So it means that everything looked fine and now it's just living. So if you reach this point, then we can assume that the compilation went well. Okay. So after that, the next step is, okay, it seems that the compilation was fine. Now let's try to run it to see if it at least works. And for that, we prepared a while ago different examples. So all these examples are just representative cases of different configurations. So you can get inside a folder and then run the code there. We didn't include an explanation because the idea is that we knew that we will do that in this tutorial. So the only thing that you need to do before the next class is just go to this folder, run the code, and check that it works and it finishes. You don't need to really check what is happening or what are the outputs. Okay, and for that, let's go, for example, to the run folder and example. Okay, and then we just type this. The idea is that for calling DeSIRe, you need to call the executable that is located in the binary file, and we just type this. So we are assuming that we are from the run folder. So then we go 2 folders back and then we enter in bin. And then we call the control file that you have inside. So here in example, you have several things, but you see that there's here a troll file. Let me try to do this. Yes, so no. Yeah, so you have here this troll file and this one. Okay. So these are the control files. So then what you need to do is for running the synthesis, just type this. It's calling and then it finishes. Okay. So we have done our first synthesis in ONNT. You will see some messages that we will cover in detail later, but basically, if you see this, then it means it worked. And then you can move to inverting, because this example also has an inversion configuration ready. So the synthesis that we have done, now we can invert it. Now we are calling the other configuration file. And you will see some numbers, and the code is doing an inversion, an ONNT inversion. And then you will see that it's iterating. So this is something that we will check, and then it finishes. Okay. So if you see this, then you can assume that the compilation worked and also the code is behaving properly because it ran a synthesis and inversion. And also you can feel a bit happy and encouraged because we have done already a non-NT inversion in just like 10 seconds. Okay. So then at this point, we have covered what I wanted to show you today. So how to compile the code and how to just execute it. But I wanted to at least show you a bit more. So then I prepared an example that in fact is the one that we are going to start from in the next tutorial. And it's here in day one run. So we are going to run it using this IDL procedure. And I'm going to run it most of the time from IDL. So I just wanted to show you also that I'm just calling DeSIRe, but I'm calling it with this keyword because I'm running from IDL. And then the idea is that then we will read the profiles. The IDL routines are also in the Dropbox folder. So here I'm including the link. And then we will read the output and we will make a plot. Okay, so then just let me go back. So we go to day one, IDL, and then we just type run, and then we'll execute. And then the idea is that it's a simple plot. So we have the wave file that in the case of SER and DeSIRe, it's defined as in milliarmstrong and respect to the core of the line. So it's not not how to say normalized. So so how I said that, Basilio? So it's respect to the line core. It's not the normalized, the general. Wait,
yeah, for the laboratory way.
To the local, it's the local, it's the local. Yes, it's the local reference. Sorry. And so then it means that it will be, in this case, it will be plus minus 2 Armstrong or 3 Armstrongs. And I wanted to have it in the proper wavelengths to just show you the calcium 8542 line. So then I take the wavelength file. I just put it in nanometers because it was in milliarmstrong, and then I added the wavelength reference that we use in the synthesis, that is 8542. And with that, I plot the Stokes I, Q, U, and V that we read. I plot them here, and then you will have something like this. Just 1 second. Yes. Okay. So the example, what is doing is just synthesizing the calcium line, very simple. Stokes I, Q, U, and V. And I added a velocity and a given magnetic field. And this, we will do it in next week. So my goal with this example is that you can go to this one. And if you want to try to change things, it's okay. You will see that most of the things are what we have covered in RH on SER. So if you have followed the tutorials, you are familiar with, so if you open this one, for example, this is one here, you will see that this is basically the SER code with some new lines here, but it's a SER control file. Or if you open the keyword.input file, you will also see that it's essentially RH keyword, but maybe we rearrange some things and we commented a lot of things. So we will go to this in detail, but for those that already we are playing with RH and SER, you can give it a try. And my recommendation is to change those files. Don't change the examples. You can do it, but these one are the ones we are going to play with from next week. So just start with this one. Okay. So then as a summary, what we have done today is compile the code. For that, we just run this sentence inside the source folder, sorry. Then we check that the compilation worked well first, checking what happens when you type that sentence. But then second, you go to the example folders or the day one run folders inside the run folder. and then you call the synthesis.troll or the inversion.troll or DeSIRe.troll, and then you run the code. Okay. And as I said, I created a separate one just for this class, and I think it's the one we will start from in the next tutorial. So then just pick this one and maybe try to play with those things, with different things, if you want. And if not, we will start from that next week. Okay. Before going back to the presentation, is there any question related with the compilation and the distribution of folders in the code? No?
Carlos?
Yes.
Yeah, so the keyword file, atoms file, and Atmos file are exactly the same what we have in RH, right?
Yes.
Okay.
Yes. So yeah. So,
and yeah, another question I have. So if you do you need the separate RH installation in order to install and run DeSIRe, or
no,
you can install it in the machine where you never had RH and still run?
Yes, for example, this is my personal machine. So I have RH21 here. So this is the one we use for the online course. But then I have DeSIRe here, but they are not interacting between them. So you just copy the DeSIRe folder where you are running, for example, where you had also RH, but they are not, DeSIRe contains all the routines that we need from RH, and they are consistent between them. So you don't need to have RH or SER distributions.
I see.
Okay.
Thank you.
Yes, and regarding your first question, yes. So the idea is that just take a look at this folder. So if you go to input, here you basically have the atoms.input that we use in RH. So it's the same. The only thing is that now it's pointing to atoms that are located in this var folder that I mentioned before. But you can see that, well, in this case, okay, I didn't change it. So the idea is that this should be like this. And this atom is the one that we are calling. Okay, so then what I was recommended, and I didn't do, is that the atom that you are changing, and in fact, this atom has the configuration that we defined in the RH class. So it's the same. So just copy exactly the same atom with your wavelength points, with your Q core or Q win. So everything is the same. And also in the case of SER, it's also very similar. So then lines are provided in the lines file in the same way as before. So you have the element, the ionization stage, the wavelength, and things like that. And then, for example, the wavelength grid is also similar to what we have with SER. So we will go one by one later on. But if you already check this in the following days, you will see that this is basically what we had in the SER tutorials and in the RH tutorials, just with minor tweaks.
So Carlos,
yes. Yes.
Sorry, I haven't been participating in a very long time.
Yes.
Just to hear that explicitly, does DeSIRe rely on a pre-install of RH and SER, or is it doing an independent install of that software?
It's completely independent. So,
okay.
so you can just download the source code and compress the file and compile. And if you have Fortran compiler and a C compiler in your computer, then you are independent. You can work with it.
Okay, thank you.
Yes, yes, yes.
So yeah, actually, some of the RH routines in DeSIRe are tailored to DeSIRe. So if standard RH would not work.
Yes.
Okay, so it is really a separate thing, or should be considered and kept separate.
Yes.
Okay.
Yes. 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 In my main folder, well, I can show you. So you have RH here, then you have SER that you can see that I have a lot of version of SER, and then DeSIRe is here. But DeSIRe is completely independent with other RH or SER folders. So it's fully consistent inside. So you can just download this, and if you have the proper compilers, then just compile it and it will work. So you don't need to have neither RH or SER. Okay.
Yes, thank you.
Okay. Okay. So then let me go back to the presentation that is here. So then my advice as a homework, just try to do what we did in the last part. So try to download the code, uncompress, check that you have the Fortran and the C compilers installed in your computer, and then just run the instruction inside the source folder, okay? And then in principle, it should compile everything. If you get an error, that it's probably that you will have them, just contact us, send a mail to me and probably also Basilio, and we will try to help you. But essentially, if you compiled in the past SER or RH and they work, it should work now. If you had issues in the past, then you will have them now, but I hope it will be fine. And then the next thing is just try to run the one of the computations, either in example or in the day one run that I will put in the Dropbox folder. And then next class, we will go slow. So we will start from that example and we will go file by file. As I said, I know that someone already used RH or SER and they know what is everything, but I will cover one by one. So we will cover SER files one by one, and we will cover also RH files one by one. So because I hope that this tutorial is also as designed, so it's completely consistent in the sense that you don't need to cover SER and RH tutorials to understand what we are doing now. If you had them, it will be easier because it's just like revising things. But if you didn't have the time to do it, it's fine. I will not point you to the previous tutorials. I will just explain everything step by step. Okay, so then this is, yeah. And after that, we will start with inversions. So next class in 2 weeks, I will try to keep a 2-week period. I think it's fine. I think I can do it. So then I hope to see you in 2 weeks in February 11th. And is there any last question or suggestion before I ask you, or I wish you a nice weekend?
Yeah.
Yeah. Okay.
So maybe I missed this part of the agenda previously, but are you going to be adding any sort of utilities in Python for those of us who are from this century and don't use IDL?
It's a good question. I think no, in the sense that what I'm doing is just running the code and reading things. So I think I will do the class in IDL as I did with SER and RH, but Ricardo has been always working in Python and he has routines for reading and writing all the files that I'm going to write and read in IDL. So I will check with him and probably he can put them in the Dropbox folder, or I will put them in the Dropbox folder. And I think those routines should behave exactly as the ones I will use. But in my case, I will use IDL, but I think those routines are already available. So I will check with him and I will try to ask him if he can provide those routines. But in my case, I will cover everything with IDL. Okay. I'm not so old. It's just that I started working with old people, so I learned all techniques. No, I understand. I understand your question, and in my case, every day I'm thinking that I should move to Python, but I lack the time. But I know Ricardo, he has been working always on Python, and when we run the code in parallel, he has to read everything the code. He has to write everything the code needs in the proper format, and also has to read everything the code provides as an output. And this he has always done it in Python. So I'm definitely sure that all the routines should be available, but I have never used them. So I want to check with him, and probably we will put them in, maybe in a few weeks, we'll put them in Dropbox. Okay, but I take note of that. Okay.
Hello.
There is a whole set of routines that can read RH input and output files.
Yeah.
There, and then that is available from the RH GitHub.
Yes. Thank you. Yeah, I think that's one question or no.
I just wanted to ask, is DeSIRE using HDF5 as additional format for writing and reading input-output files, or is it just using binary format?
I think
HDF5 is basically independent of any Python or
I think
any
ASCII files is
ASCII file.
Yes, I think DeSIRE is ASCII, right, Basilio? Or Basilio left, I think.
Yeah. Yes.
Yeah, you're
It's
here.
ASCII.
Yes,
Yes.
it's ASCII file. So
Yes.
Thank you.
yeah. Okay. Any additional question? Okay. So then, if not, just enjoy the weekend, and I hope to see you in 2 weeks. So let me stop sharing. Okay. Thanks a lot, everyone, and I'm happy to see you here. Okay.
Thank you.
Thank
Bye.
you.
Take care.
Thank you.
Bye.
Thank you.
Bye.
Bye.
See you. Bye.
Huzzah!
Bye.